Hello. I think we're about ready to get started. So if people could find their seats. First of all, I want to say welcome. My name is Brian Weiner. I'm the chairman of the physics department here at OSU. And on behalf of our department and the university, I want to welcome you to the 55th Alpheus Smith Lecture. So this is something we've been putting on for many years. It's intended to bring distinguished scientists, such as the one we have here tonight, to campus to talk about some of the interesting scientific subjects and studies that are going on around the country and around the world. And this lecture is named in honor of a professor who was here at Ohio State. His name was Alpheus Smith. He actually joined the faculty in 1909, and he was a physics professor, and he became chair of the physics department in 1927. He then became, in 1938, the dean of the graduate school, and he retired from that post in 1946, but that is what I refer to as his first retirement. He was immediately asked to lead the OSU Research Foundation and be the president of that foundation. And so he sort of oversaw a really expanding role of the university in terms of being a research university from the late 1940s into the late 1950s. And so he retired for the second time in 1958. And then through the generosity of his family and friends, they endowed this lecture, and in 1960, there was the first Alpheus Smith lecture, and here we are many years later at the 55th. And tonight, our speaker is Dr. Duncane Haldane. He is a Sherman Fairchild University professor of physics at Princeton University. He received his undergraduate degree and PhD from Cambridge. Earlier today, I was looking through all of his honors that he's got listed, and I could go on and on and on. I'm not sure you want to hear all of them listed, so I'm going to give you a sampling. One of the things that can honor a faculty member is being elected as a fellow of a scientific society or academy. And I just want to give you a few of the academies and societies that our speaker is a fellow in. He's a fellow in the American Physical Society, the Royal Society of London, the American Academy of the Arts and Sciences, the American Association for the Advancement of Science. He's also a recipient of the Oliver E. Buckley Condensed Matter Physics Prize of the American Physical Society. And oh, by the way, he shared the 2016 Nobel Prize in Physics. Most recently, in May, he was actually elected to the National Academy of Sciences. And so those are just a few of the honors that our speaker has tonight. And he will be talking to us about entanglement, Einstein's gift to quantum mechanics. So please join me in welcoming Dr. Haldane.
Well, thank you. It's a pleasure to be here, and I have long-standing research relations with at least one of your faculty members, Jason Ho, and also Nandini Trivedi. And so we have a lot of history together. And in fact, Jason was around at one of the earliest conferences I went to. He was actually reminding me of things about that. But what I'm going to talk to you about is two things. I'm going to talk a little bit about quantum mechanics and Einstein's contribution, which I will say his gift to quantum mechanics of the notion of entanglement. And this is because this very curious quantum mechanical property of entanglement turned out to be the crucial ingredient in the things I and other people who got the Nobel Prize this year discovered. And this has gone, we didn't realize it at the time, of course, but this has emerged as this field has developed, and now this has turned into a very thriving field where people have dreams of a new quantum information technology based on some of these entanglement properties. So, let's say in public lectures about quantum mechanics, the usual thing people talk about is the Heisenberg uncertainty principle, which, roughly speaking, says you can't, if you try to measure something or look at something, you inevitably interfere with it and change it. So this is this famous property that one can't measure a property of an object without affecting it. And that's not what we're going to talk about, because there are a number of other important features in quantum mechanics which come out. And I would say there are at least two other key ingredients in quantum theory. And the first of those, which is absolutely fundamental to our interactions with the world around us, is the Pauli exclusion principle. It's not at all implied by the Heisenberg principle. It's a completely separate thing, a property of quantum mechanics. And this is Wolfgang Pauli. And the other thing which I'm going to stress here is the much more obscure property of entanglement that Einstein first pointed out with two colleagues, Podolsky and Rosen, at the Institute for Advanced Studies in Princeton in 1935, where Einstein ended up after leaving Germany. So Einstein, of course, is most famous for relativity. And so he had a very great year in 1905. He actually did 3 important, completely unrelated pieces of work. One was, of course, the special relativity theory with the famous formula E equals mc squared. But he actually he also did an early contribution to quantum mechanics, and he discovered he gave an explanation of the photoelectric effect, what happens when the electric current you can get by shining light on metals, and that's of course what actually prevents your garage door from chopping your head off. There's this little light beam which, if you interrupt it by standing in front of it, you'd interrupt the photoelectric effect. So it's got great practical importance in your garage door, but in a lot of other things. And in fact, it was the subject he got his Nobel Prize for. People would probably think he got his Nobel Prize for relativity, but in fact, he got his Nobel Prize for this is actually the second contribution to quantum mechanics after Planck discovered the secret of the black body radiation law and why the sun is yellow. So he also did some work, another piece of work which is not mentioned, to do with Brownian motion, the random motion of particles suspended in a fluid, which actually was a way to demonstrate the existence of atoms directly by looking at the effect of collisions between molecules in the liquid and particles of pollen grains. So anyway, he did a lot of things, and it looks like he's done something important every 10 years. After his 1905 trifecta with the 3 things, he ended up, 1915, he completed his theory of relativity by including gravity, the general theory of relativity, which is a geometric theory of gravity which completely changed our understanding of gravity. And of course, this year's Nobel Prize is the final direct confirmation of these waves, gravity waves. So just as light is electromagnetic waves that can travel through space, gravity, predicted in Einstein's equations, but not in Newton's equations, can have waves of gravity, gravitational waves that travel, and these were finally experimentally detected after 40 years of attempts to do it a year or two ago, and is rewarded this year. So I'm kind of like Miss America, you know, the crown just got taken away from me to the new people, right? So in the gravity theory, he actually introduced something called the cosmological constant. When he found his original gravitational equations, which are this kind of, it looks rather complicated, but it's a pretty simple equation. All these symbols mean something. He found that the universe, gravity would always cause the universe to want to eventually collapse, or at least to slow down. So he couldn't find a stationary state where the universe stayed stationary. And he didn't like that because at that time it seemed too much like religious ideas about the creation, the Big Bang. So at the time people preferred, the scientists at that point wanted to have a static, stationary universe. It sounded kind of more elegant to them. So he added this extra term to his equation that balances gravity, a kind of anti-gravity term that causes things to move apart, while gravity causes things to move together. And the only thing was, about a couple of years after he added this term, Edwin Hubble at Pasadena and at Caltech did observations of the galaxies were receding from us and actually found that the universe was expanding. And so Einstein at that point called this term his biggest mistake. And one would like to have pretended he never added it to his theory. But actually, only about 10 years or so ago, we discovered that the universe was not just expanding, but it was actually, expansion was accelerating with time. Without an extra term like this, it could have started off expanding like when you throw a ball in the air, but eventually the ball would come back down again, except if you threw it up extremely fast, then it would keep on going. It would slow down, but keep on going forever afterwards. But that's not what happens with the universe. It's actually expanding. The rate of expansion is accelerating. And so now we actually believe that there's some term like this in the equations. So we found out that Einstein's, what he felt was his greatest mistake, was actually an amazing insight and is probably at the root of dark energy, this mysterious force we found out. So after 1915, he actually did something more important for another thing which was important for quantum mechanics. He discovered something which is called Bose-Einstein condensation. Bose, an Indian physicist, had some initial aspects of that too, but Einstein completed it and came up with a notion of Bose-Einstein condensation. And this has turned out to be something that's now experimentally observed in very cold, dilute gases of atoms cooled down to incredibly low temperatures by shining lasers on them to kind of decelerate them. And this has actually been the subject of at least one Nobel Prize, and will probably more. A lot of very interesting properties of quantum mechanical states of atoms emerge from this Bose-Einstein condensation. However, his attitude to quantum mechanics started to change after this period. And he noticed there was really a fundamental problem in merging quantum mechanics with his gravity theory. And this is a problem that still exists today. String theory and other attempts are trying to find a way to do a quantum theory of gravity, but it's resisted. So his attitude to quantum mechanics kind of cooled down. And in 1935, he and these two co-workers noted that quantum mechanics had a property, this entanglement property, that he thought was so strange, it had to mean that quantum mechanics was wrong. And I would call this his second biggest mistake, because finally, many years after his death, when it was able to be checked, quantum mechanics passed the exam 100%. Einstein's worries about quantum mechanics and the fact it seemed to be crazy incorrect. Quantum mechanics still may seem to be crazy, but that's the way it is. And I would call this his second biggest mistake, which is also a brilliant mistake, because he put his finger on a crucial property of quantum mechanics. He thought it was so weird that quantum mechanics must be wrong, but it's actually a property that people before hadn't realized was such a strange property of quantum mechanics, and we now know it's true. And in fact, this entanglement property today has turned from a kind of abstract philosophical objection to quantum mechanics into a practical thing that people are trying to create and store, and it's believed to be, in some sense, the fuel which may drive the future technology of quantum information processing. So it started off as abstract thought and debate, and that's turned into practical things which probably will have important technological implications. Okay. So it's his second biggest mistake, but Einstein is such a great man, his mistakes are also tremendously instructive for everyone to study. Okay. So I wish he'd made a few more great mistakes so we'd have more things to follow up on. So as I say, despite making this early contribution, which actually got him his Nobel Prize to quantum mechanics, by 1935, he basically had rejected it. He thought it could be some kind of approximation to a better theory but it couldn't possibly be the true theory. And as I say, he called this entanglement property, he didn't use the word entanglement, he called it spooky action at a distance, or in German called spukhafte Fernwirkung, which is apparently a translation of spooky action at a distance. And one of the other founders of quantum mechanics, Erwin Schrödinger, he thought that was a little bit of a pejorative term, and he said, let's call it Verschrankung, which apparently is a German word which has been translated as entanglement in English. Okay. So as I say, quantum mechanics has always been kind of mysterious for the general public, and much more, in some sense, much more mysterious than relativity. You know, people can get used to stuff about clocks and things not moving faster than the speed of light, but in some sense, quantum mechanics is much stranger than relativity. But physicists actually find it mysterious too, but they kind of, as a working physicist, I'm not going to spend my time worrying about whether quantum mechanics is true or not. It actually does seem to have passed all the tests, and we're actually trying to do things with it. So, and it's actually confirmed as the true description of the world. Now, it doesn't really correspond to our everyday senses, because to actually understand the importance of quantum mechanics, it really determines the structure of very small things, atoms, and which are kind of below the kind of length scales that we're able to see with our everyday senses. So you need to have scientific equipment to look at very small things. But basically, you cannot understand atoms without quantum mechanics. You cannot understand molecules, chemistry, or the regular matter that we're all made of. So there's no basis for the atom to exist if there wasn't quantum mechanics. So the existence of atoms was a great concern. What exactly atoms were, and if they even existed, was a great concern in the 19th century. In fact, Einstein's work on Brownian motion was one of the first things that gave a very clear proof of the existence of atoms by looking at the effect of molecules colliding with pollen grains, which you can see under a microscope. Right? But anyway, so originally the Einstein objections to entanglement seemed like a philosophical issue for philosophers to debate. And indeed, part of this discussion involved things like, is quantum mechanics compatible with free will? Which sounds exactly like the kind of question that philosophers like to discuss, right? But it's not really a very practical area of inquiry for kind of working physicists, you know. So you can sit around and have coffee and discuss, you know, does free will exist? And these are kind of the questions that we, as practicing people, don't deal with. But as I say, today it's experimentally confirmed, and it's well on its way to having a technological significance. So there's some practical, it's not just some empty philosophy issues. Okay, so let me just tell you one thing which I hope you might take away from here, that one of the properties of quantum mechanics that you might not be familiar with, but is actually a fundamental part of our everyday life. And again, it's this Pauli uncertainty principle I mentioned as an independent quantum property that says that two particles of a kind called fermions, and most of the matter we're made of is basically made out of fermions. Two fermion particles, such as electrons, cannot be in the same quantum state, which roughly means they can't be in the same place. Okay. And now, of course, the force which we're one of the forces which we're aware of in our daily life is gravity, which is pulling us down. And gravity is pulling us towards the center of the Earth. But the atoms out of which we're made are about 99% empty space. You know, there are little electric charges in them, but most of the space in the atom is totally empty. So it's a very so why don't we just fall through the floor and head towards the center of the Earth where the gravity is pulling us? And of course, this is the question. If there was nothing to counteract the gravity, we would just fall directly downwards. Or if there was only the gravity force, which you learn in high school or whatever is m times g, the mass times the gravitational field at the center of the Earth's surface, we would just fall. So it's quantum mechanics that prevents us being sucked down to the center of the Earth and keeps us from falling through the floor. assuming the floor is being built strongly enough, of course. So Newton's interpretation of why we don't fall through the floor is that the gravity force is counteracted by an upward force, which he called the normal force. Normal not because it's kind of not unusual, but it's actually normal because it means at right angles to the floor, vertically upwards. And if I look at Einstein standing on the floor, there's a gravity force which acts at his belly button, I guess, his center of mass, and pulls him down. And the normal force acts on the soles of his shoes, presumably half of it on one sole and half on the other sole, and pushes him up. And if you've ever done mechanics in high school, or in physics 104 or 103 or 102, one of these classes, you actually have to, you have to balance the force. If Einstein is stationary and is not falling to the center of the Earth, the forces, the two normal forces have to add upwards, and the gravity force downwards have to add up to 0. Otherwise, he would be either accelerating downwards or accelerating upwards. So Newton came up with, Newton took the existence of the normal force as an obvious fact, and some experience that you have in everyday life, that you put your foot on the floor, you feel the floor pushes up against the weight of you pushing down. And it doesn't need an explanation. And in fact, it does have a fundamental explanation that when you go back to quantum mechanics, because of the Pauli exclusion principle, this neat principle that says that two electrons can't be in the same state. So what's actually happening there is, in your shoe, there are a load of atoms, which are basically, an atom is somehow a little box of electrons. The center of the atom, the nucleus, is where almost all of its mass is concentrated. These are kind of particles called neutrons and protons bound to the nucleus, but they actually don't do much in matter. They may vibrate a little bit about their positions, but they basically are glued in place. But the things which could be mobile are the electrons, which are attracted by electric charges. They're negative charges, and the nucleus is positive to be bound to the electron, bound to the nucleus. So there's electrons which are bound to the nuclei, which are welded together in your sole of your shoe, and there are electrons which are bound to the nuclei of the atoms, which are glued together in the floorboards or the concrete underneath your feet. And it's actually the fact that this set of electrons doesn't want to be in the same place as the other set of electrons that repel each other. So it's not an electrostatic repulsion, it's not electric forces that are repelling each other, it's this quantum mechanical principle that they can't be in the same place that causes the thing. To actually push them together, you'd have to push one of these into a much higher energy state of the atom, and there's energy gaps against that. So it's basically the Pauli exclusion principle is such a fundamental principle for everyday life. And it's actually, of course, the matter we're made of are molecules. The atoms are glued together in molecules by chemical bonds. And chemical bonds have the interesting property that chemical bonds essentially involve two electrons. So to make a chemical bond, you actually have to put two electrons in the same place. Well, somehow the Pauli exclusion principle, at first sight, doesn't allow that. But actually, there's one extra ingredient the electron has besides being a little charge particle. It's a little spinning charge particle. And so to describe an electron state, the principle actually doesn't say the two electrons can't be in the same place. It says they can't be in the same state. And the state of the electron is described not just by where it is and how it's moving where it is, but also by this additional little degree of freedom, the spin, which is kind of like a little magnet. So an electron behaves like a little charge, but it's also like a little bar magnet. It's got this, and it points in the magnetic, the north pole or whatever would be in the direction of the spin. So a chemical bond actually is made of two electrons in the same place, but they have to have, their spins have to be different. And this is actually the origin of entanglement. The two electrons in a chemical bond are fundamentally entangled by this quantum property. Well, anyway, so you could actually, here's the old model of the atom, probably due to Bohr. You've got the nucleus, and you've got these little electrons going around it in little orbits. A more modern view of the atom is a kind of box of electrons. The nucleus attraction to the nucleus forms a kind of box that contains the electron, and they are in a kind of cloud. And now when you excite, at least when you have highly excited atoms, you can actually visualize the electrons. Now this is actually a real image of a highly excited hydrogen atom, which consists of one electron going around one proton. And this one is highly excited, so it's actually going around in some kind of, this picture would have it going around in an orbit. It was very large, but it's large enough that you can actually visualize this and now take a photograph of the electron cloud distribution. So electrons is principally, this high energy electron is principally concentrated, well, it's got a part which is, it's got wiggles in its state, and there's a part which is out here at the furthest part of this shell. Okay. So so as I say, the electron has a spin. You can think of it as a little rotating top, like a child's toy. It's spinning, and the magnetic moment or magnetization is along the direction of spin. There's a famous right-hand rule that you have to use in electromagnetism, and it actually converts the direction of rotation, which is the way my fingers are pointing, to the direction of the spin, or the so-called angular momentum. Okay. So the electrons have this, you can think of it as a particle which has a little arrow, and the chemical bond has two electrons in it. They're kind of in a cloud in between the two nuclei that they're gluing together, but one electron, if one electron has its spin up, the other electron has to have its spin in exactly the same direction, but downwards, opposite direction. So the crucial point about the chemical bond is whatever the direction of the first electron's spin, the spin of the other electron is pointing exactly in the opposite direction. So what is the issue with that? That would seem to suggest that a chemical bond has a particular direction in it associated with the direction, the two opposite directions of spins. But no, the chemical bond doesn't care about what direction these things are in. It's a feature that they could be pointing in any direction. Whatever the direction the first electron points in, it's always opposite to the second one. So actually, quantum mechanical states are a little bit complicated, because to actually even understand quantum states, you have to, people have learnt about whole numbers and then fractions and real numbers. There's a thing called complex numbers, which you need to learn if you want to do quantum mechanics, and if you want to do lots of things in electrical engineering, it's good to know complex numbers. But basically, the electron's state is represented by this so-called complex number, but it's got a property. You can write it as electron 1 up, electron 2 down, minus electron 2 down, electron 1 up. It has this property that if I switch the two electrons around, this number changes from plus to minus, plus a complex number to minus a complex number. So you see in this, if I switch these two things around, I get a minus. And that's actually the more correct statement of the Pauli exclusion principle. But we can write this wave function, this state of the electron. It could be up, down, and down, up. It could be left, right, and right, left. Or it could be this way I've drawn it at an angle. These are all descriptions of exactly the same state of the chemical bond. So actually, although the spins of the two electrons are opposite to each other, we can't say which direction the spins are in. In fact, we can only attempt to measure it, and to measure the spin direction, we have to choose to measure it relative to some axis. And so we will end up, if we measure it relative to the vertical axis, we'll find up, down, minus, down, up. If we measure them relative to this oblique axis, I would have them, it could be right, left, minus left, right, or whatever. So it's a curious thing, and this is the heart of entanglement. Okay. So the length of the chemical bond is very small. It's 1/10 of a nanometer. Well, what does that mean? There's actually 1 billion nanometers is 1 meter, and a meter is about 40 inches, right? So it's a very, very tiny scale, a billionth of a kind of scale that we can imagine. And Einstein was not worried about the chemical bond. He was worried about the theoretical possibility of creating states where you, instead of this very narrow, very tiny object, the chemical bond of the two electrons, by imagining what happens if you could stretch it to make it very, the distance between the two particles to be very, very big. And quantum mechanics says you can still make a state in which when particle 1 is pointing in one direction, the other particle is always pointing in the other direction. And so this was actually the problem that Einstein, Podolsky, and Rosen were worrying about. So they didn't worry about chemical bonds because when the chemical bond is strongly protected by the energy needed to break it. You have to put in a lot of energy to break a chemical bond. So shining ultraviolet light on it will break it. That's why you have a problem going out in the sun. The sun can damage your skin by breaking chemical bonds in the cell, structures of the cell in your skin. But when you try to make this pair of electrons which are kind of entangled, very far apart, they become, this energy protecting the chemical bond goes away. It's very, very fragile. And the thing is, if I make this, so I'm going to represent an entangled state by a little dotted line between these two electrons, because I don't really want to say it's up, down, or down, up. It's kind of an arbitrary combination. It's whatever you want, but it's entangled. And the basic problem of entanglement is the fragility means that this very far apart entangled pair is very susceptible. If there was another electron somewhere near this one, it would mess this bond up, it would destroy the quantum entanglement, and instead this electron would end up entangled with the nearby electron. And this is called the decoherence process. And this is the main obstacle to building quantum computers, because we need to use the entanglement to drive information processing protocols, but we have to protect the information against being lost by decoherence with the environment. So Einstein and Podolsky and Rosen, they thought of what we now call an EPR pair of widely separated particles with this entanglement. They thought of them as being created by the following thing. We start with a pair of electrons in this so-called singlet state, in this entangled state, sitting inside a little box. And they thought, well, which would be the chemical bond or something. And then we switch off the walls of the box. And in fact, one of the principles of quantum mechanics, the Heisenberg uncertainty principle, says that if the particles are confined in the box, we don't know what their momentum is. In fact, the smaller the box we confine them in, the larger the uncertainty in the momentum, which is the mass times the velocity of the electrons. So once you switch off the box, by the symmetry of the box, the total momentum of the system is 0. But when you release the box, release the electrons, the momenta have to add up to 0, so they have to be moving in opposite directions with exactly the same velocity, speed, and so they will fly apart in opposite directions, and which is actually due to the fact that the momentum has to equal 0. But there's a conservation law that says the momentum doesn't change unless a force acts on these particles. So they'll fly apart in opposite directions, and this is the notional pair, and they'll keep on going for a long distance, and they'll remain entangled until one of the electrons kind of meets something else in the environment a long way away and loses its entanglement. So if they can fly apart without meeting anything else, they maintain this perfect entanglement, even if they're like light years away from each other. And this is what Einstein just didn't like. So actually, in 1935, there probably wasn't too much going on that day in the news, but one of Einstein's collaborators, Podolsky, he went and told this story to the New York Times that Einstein has destroyed quantum mechanics. And so there was a headline on New York Times saying, scientists and two colleagues find it's not complete, even though correct. Which Einstein thought it gave the correct answers, but it wasn't philosophically correct. And obviously there was he says a fuller description must be possible, and they believe a whole description of physical reality, which is not quantum mechanics, will eventually be discovered. And as I say, Einstein worried that the issue was that until you measured the direction of the spin, he thought the spins had to have a fixed axis of direction when this particle split apart. So he thought when they split apart, they had to be either like that and that, or like that and that, and he couldn't accept that the direction of the spins was not fixed until you actually did a measurement. And you also have to make a choice of measurement axis. And then you're worried about, what happens if you decide the free will aspect of the thing is, what happens if you make the choice of which axis to measure long after they split apart? So this was the problem. So the spin, as I say, the EPR particle pair flies apart. The two observers, a long way away from each other, can have previously agreed they're going to use this measurement axis, and if the same measurement axis, and so if they measure, if one observer measures the electron to be up, the other spin up, the other one will down. And if they chose this axis, if the first measurement said it was that way, the other experimentalist would always find it in the other direction. And so this is perhaps okay if you said they'd already made the decision which axis to measure, but suppose the decision was actually made after they flew apart. And they worried about this issue. And Einstein's quote on this thing, he says, so making a choice of a measurement axis is supposed to be an action of free will. I think I could flip a coin, or I could say, well, I'm going to choose up or down, or right or left. But anyway, Einstein felt this was a totally unsatisfactory thing, and his basic famous statement about this is, God does not play dice. That was his rejection of quantum mechanics, which said there was a certain probability of finding one thing and then finding the other thing. He thought the directions of spins had to be fixed once and for all by the time the electrons moved apart. And he called that local reality. So he believed in so-called local realism. Okay. So as I say, he came up with this, but other people started thinking about this. First David Bohm, and then more importantly, John Bell, later on in the, I guess, 70s or 60s, started coming up with a much clearer version of Einstein's paradox by saying, well, suppose you one experiment measures up or down, and the other one measures right or left. Well, those are completely incompatible. One measures 45 degrees and minus 45 degrees. And he came up with a set of inequalities that Einstein's idea of local realism, that everything was determined already when the electrons flew apart, would put a bound, said that certain measurements could never occur. And when this actually got tested by a French experimentalist, Alain Aspect, in 1982, he finally carried out, but after the death of John Bell and the death of Einstein, he carried out these experiments, and he confirmed that quantum mechanics the experiments violated the bounds that classical realism set, that Einstein would have said had to be there by common sense, and it showed exactly 100% agreement with the quantum theory. So Aspect's experiment didn't use electrons, which are much more fragile against meeting charges elsewhere, but he did the same thing with light, photons, and just as electron has spin up or spin down, the photons have two states of polarization. For example, your sunglasses filter out horizontally polarized light, which gets reflected by glare off the road and lets the vertically polarized light through. So I could spin, choosing the vertical axis for spin would be like measuring linear polarization, which would either be up, down, or right, left. Or there's another kind which is called circular polarization, and that would be like measuring the right-left thing. So there are different choices you can make of measuring the photons. And in fact, the Einstein-Podolsky-Rosen EPR photon pairs have now been, in fact, this says they've been measured and proved, entanglement proof when they're separated by oceans. In fact, China, who's investing a great amount in this technology, so I hope we don't kind of fall behind in this thing, have actually made a big deal because they've managed to repeat this not just across the ocean with an optic fiber, but actually by transmission to satellites in orbit. So they've actually managed to send quantum cryptography pairs, transmit keys for quantum cryptography in an uninterceptable way using EPR photons to satellites. And pretty soon this is going to be checked out by things in the distance between the Earth and the Moon and the so-called Lagrange points. So this is absolutely established now. So the era of discovering what kind of cool things can be done with quantum mechanics, partly based on this entanglement, is actually only just beginning, right? So it took us a long time to start to realize these informational and entanglement aspects of quantum mechanics that can be exploited for useful things. And we're now just beginning to get this kind of exquisite control of quantum states. Previously, our experiments were like bashing something with a hammer and seeing what the pieces flew away. Now we're kind of taking these quantum states and trying to nudge them and poke them in different directions and try to make them do interesting things without destroying them. Okay, so as I said, the new ingredient in all this is actually this development of quantum information theory, which is really an outgrowth of this Einstein, Podolsky, Rosen, and John Bell problems. And so this is actually what we're going to. So what is information? Classical information, the usual kind, which is, by which I mean the non-quantum information that your today's computers and smartphones and everything work on, is stored in the form of a little switch. It's either on or off. And in terms of spins, you can think of it a large number of spins which are all up, and I do something rather violent to them with a magnet to cause them all change direction, and that would switch the switch off, and they're all pointing down. So the quantum information, on the other hand, is stored in the state of one spin, not a large number of spins all parallel to each other. And this has been called a qubit because a bit this is the original classical bit, which is on or off, or 1 or 0. So qubit, the spin can be pointing in any direction on the sphere. And this is called the Bloch sphere, and all the kind of quantum information processing basically involved can be reduced to what you can do by moving the direction of this spin from vertical to horizontal to towards you, to right or left, or at arbitrary angles. So this is the information, and there's a lot more sensitive information I can store in this thing than just up or down with the original form. Okay, so what was my work got to do with this? Well, topological quantum matter is what these Nobel Prizes, the last Nobel Prize was partly given for. And to the best of our, as I say, to the best of our knowledge, we've known the quantum mechanics laws for many, many years, but I would make the point that just because we can write down a set of equations which never have been, we know to be true, all attempts to kind of falsify them or find generalizations have failed. They seem to work 100%, but just because we know what the equations are doesn't mean we know what you can do with what they can do. And similarly, Maxwell discovered Maxwell's equations, which are now really the complete equations of electromagnetism. And at the time, there's a famous quote where someone asked him, well, this is all very interesting, Dr. Maxwell, but what's it useful for? He said, I really don't know right now, but I do know one. It was a politician. I don't know right now, but I do know that at some point in the future you will tax it. So it's taken a long time to develop, all the things we can do with electromagnetism, and so same thing with quantum mechanics. Now it's taken this long time to really start. This information aspect of quantum mechanics is just starting to emerge, and we're really starting to see what we can do. So around 1980, when my work was started on this, condensed matter physicists, condensed matter is a fancy word that replaced solid state. It used to be solid state, but then everyone said solid state meant a transistor radio. So they thought it was not fancy enough, and they changed the name to condensed matter, so you could also include liquids as well as solids in this. It means liquids and solids, but not gases. Anyway, condensed atoms which are close together, basically. So condensed matter physicists thought they had a basic understanding of condensed matter physics. But of course, every time people think they have a basic understanding and there's not much left to do, that actually is just a signature of their own ignorance, right? And in 1980, there were two weird properties, two examples of properties which were kind of weird, that didn't fit into the general idea of things at that time emerged. And now we know these two things are, the weirdness was because they involve quantum entanglement in a significant way, and in another way, in this way I'll call topological, which I'll come to in a minute. So these were like the tips of the iceberg. The two of them, one of them was part of my work, which is to discover something strange in the theory of some very obscure topic that sounds very obscure, little chains of magnetic atoms and what kind of quantum state they can be in. And the other thing was an experimental discovery. This was a theoretical discovery. The other thing was an experimental discovery that there was some amazingly accurate some things you could measure were exactly fixed by whole numbers, basically, in an amazingly accurate experiment. This is called the quantum Hall effect. And if you have the analog with the iceberg, the tip of the iceberg, we have an iceberg with two tips on it, but actually there's a whole hidden world underneath this, which has emerged more and more in recent years and has really taken off in the last decade. And this is what we call the world of topological quantum matter. So what is topological, or topological matter? That's a fancy piece of mathematics, topology, but the fact it's got some applications to real materials and matter is actually tremendously excited many young people these days. The fact there's some abstract and deep underpinnings, and you can actually go and look at materials that chemists can make, and then you can study them, and you can see this stuff, which was completely unexpected and missed for many, many years until theory kind of said there has to be something called topological matter. The fact this has come out has been very exciting because people there's this very powerful math that they can talk about and show pictures. And topology has nice pictures to go with it. So topological matter differs from ordinary matter because it's got some properties you can describe in terms of whole numbers, like 1, 2, -1, 3. So a lot of things in physics and mechanics and other things, you have to do precise measurements. You take your ruler and you measure this is 3.42 centimeters or inches long, and it weighs 5.34 grams, and you have a very accurate balance to measure it. But not many properties actually come in whole numbers, countable ones. Okay, some of these properties have negative numbers, so it's not quite the same as simple whole numbers. But basically, notionally at least, ordinary matter is described by kind of boring numbers, which could be indifferent depending on the context, 0 or 1. Now, of course, people point out the number 0 is not a boring number. It took a long time to discover there was a number 0, but the Arabs discovered it, right? The Romans didn't. That's why we use Arabic numerals, because Roman numerals are completely impossible to do mathematics in, because it doesn't have a 0, among other things. So anyway, ordinary matter, so states of matter which are described by different whole numbers can't smoothly change into each other. If they've got some matter which has the property measured by 0, which means it's boring, and some other region of my crystal or my lump of stuff has the property -2, there can't be they can't smoothly go into each other. There has to be a boundary, a wall, where the number 0 changes sharply from 0 to -2. And that's part of the stability of topological matter. So regular matter, the stuff that before 1980 was thought to be well understood, is like crystals. Usually crystals, it could be liquids. But in a crystal, there's kind of the atoms are arranged in a nice little ordered pattern, which repeats itself, and that's called conventional solid order. And crystals and most solid matter, I mean, I'd have to worry about wood and things like that, but most things like rocks and metals are made of crystals. And there's nothing special at the edges of these crystals. It's just repeating, like adding little dominoes and building up this pattern of this little rigid pattern. And people studied the patterns, the order, so-called, of the crystals in great detail. While the topological matter, actually, for example, the quantum Hall fluid, which is one of the things that von Klissing discovered, is topologically ordered liquid. There's actually nothing special that looks that different from other liquids in the middle. But if I look at the boundary, it's got some local modes, some excitations that can travel in one direction only around the boundary. So if I tickle this liquid, I can make stuff that the disturbances on the surface travel only in one direction, not the other direction, which is pretty strange, right? Okay. So what's unusual? The unusual thing is, in general in topological things is very typically there's something strange happening at the boundary where the topology changes. So as I say, topology, so to make a point for technological things, this fact that they're classified by whole numbers and whole numbers can't change easily makes them quite possibly useful for technological things. If your technology is based on a topological property, you don't need the ultra clean room that you do for silicon technology. To make a computer, you have to grow stuff on a silicon wafer. These wafers have to be grown in an ultra clean room with people full of white suits and everything. A single speck of hair or a bit of spit or something that went onto the wafer, a dust particle will ruin it. They'll have to throw it away. It's no use for building the computer on because a little bit of dirt ruins these things. But you can't ruin a topological property unless you do a large amount of dirt, right? So they're intrinsically robust against damaging. The damage has to exceed some finite amount before it causes a loss of the topological properties. Okay, so the classical example in mathematics of topology is a classification of a closed surface by the number of holes. Okay, so holes come in whole units, right? And whole number units. You can't have 0.36 of a hole. You can count the number of holes in something. It's either 1 hole, 2 holes, 3 holes. There's no minus 3 holes, but they come in whole number units, and there's no such thing as half a hole. And there's actually a formula that some of us might remember from high school. We had to kind of learn it and memorize this. The surface area of a sphere is 4 pi r squared. And there's another formula for the volume, and most of you have probably forgotten that once you left high school and finally took the last of your math exams. But this actually, one of the greatest mathematicians, he's probably regarded as probably one of the greatest since Archimedes or Pythagoras or whatever, was Carl Friedrich Gauss, a German mathematician around 1800. And he discovered a very simple fact. He discovered, you take this formula that the surface area of a sphere is 4 pi r squared. Now a sphere has a curved surface. It's curved in 2 directions. And there's a formula for what's now called the Gaussian curvature of the surface of the sphere. It's got the same curvature at all points, and that curvature is 1 over r squared. So Gauss discovered this, what he thought was the most amazing fact that he'd ever found in all of his career in mathematics, was that 4 pi r squared times 1 over r squared was 4 pi. Now this may sound a slightly obvious conclusion. However, it's trivially true for the sphere. Suppose I take the sphere and deform it into a football, which is kind of elongated, right? The curvature is no longer constant on the surface of the sphere, and that's a much worse homework problem to be given by your math teacher to work out sum the curvature. And even worse, you could turn it into a banana. Even more difficult to do this thing. Maybe with a computer you can actually do it more easily these days, but you certainly can't do it with pencil and paper and anything you learn in high school. But he discovered the integral, the area, the curvature weighted by the area was always 4 pi, provided there were no holes in it. But then he went on to find out that if I put 1 hole in it and make something like either a donut or a coffee cup, it's got 1 hole in it, the number was not 4 pi, it was 0. And I put 2 holes in it, it's minus 4 pi. 3 holes in it, it's minus 8 pi. I think you probably get the sequence. You start off with 4 pi, and each time you add a hole, you subtract the 4 pi. And it's a whole number times 4 pi. And the bagel has the same, you could turn the bagel into a coffee cup. It's got the hole becomes the handle. This is something that in Sweden they were calling a Swedish pretzel. It's actually a Santa Lucia bun, and usually the holes actually get filled in when they bake it. But that is equivalent to this kind of cup, which I learned is called a loving cup. And this is the real pretzel, the so-called German pretzel, which actually has 3 holes in it. And well, I couldn't find this. I found this thing which I've heard some people suggest might be called a California loving cup. I don't know what it's, I'm not sure what its real name is, right? But anyway, so as I say, before 1980, okay, this is a repetition. So as I say, in recent years we discovered this entanglement property and this property of the quantum states which have entanglement. So it's the entanglement can be measured by some kind of integral, and it turns out that the Gauss's formula, in a much, much more abstract sense, also applies to these quantum mechanical states. So again, the entanglement state is topologically different. A trivial state, so-called, is one which you can just regard. You can do a measurement of anything on the left side of this, and it doesn't really affect anything on the right-hand side. And you call that trivial entanglement because there's no real quantum connection between any part, this part and that part. I can separate it. But if I take one of these topological matter things and try to cut them, to separate them out, they actually have this edge state or something on the surface that goes around it. So I try to pull it apart. It'll resist for a little bit, so it'll start to form holes. But when it suddenly splits, the entanglement between the two is broken, but the broken entanglement will kind of result in these non-trivial edge states, this system on the things on the edge which will kind of terminate the entanglement. So it's a bit like you try to make you've got a bar magnet, you try to get the North Pole and separate it from the South Pole. So you chop the magnet in half, but all you've got is two magnets, each of which has a North Pole and a South Pole. Try as you can, you cannot make a magnetic monopole which is people have desired for a long time, by chopping a bar magnet into smaller and smaller bits. And this is not that. The bar magnet is actually more like the regular solid stuff, but the entanglement properties are something similar. Okay, so basically, topologically non-trivial states of matter can be formed, you can visualize by making solid matter by bringing atoms together from a large distance and making a blob of atoms and combining them. And basically, if the matter is non-trivial, nothing very important happens, really, if I bring the atoms together. There may be some rearrangements of things, but essentially, by bringing atoms together, you can make trivial matter. But if something along the way happens, they start to get entangled and change, something happens along the way suddenly, then you change and you make this non-trivial matter. And non-trivial matter does all kinds of weird things. I mean, one thing you find inside topological matter is, for example, you can make electric charges which are half the charge of the electron. You might say, well, the electric charge is 1, and we know electrons are indivisible. But in fact, if I have a system where the charges are arranged in a kind of line, 1 electron, no electrons, 1 electron, no electrons, and this is held together by condensed matter forces, if I remove an electron from the middle, I've actually got a missing electron here, but now I can start to rearrange these black dots to move the thing aside, and you see I've actually created 2 half electrons. And that's very typical of the weird things you start to find in topological matter. We used to think the only place that weird charges happen was, we know that quarks have 1/3 charge, but they can never be separated in particle physics. So there's all kinds of strange things happen inside topological matter. Okay, so one of the things I did in heavier atoms, when groups of atomic orbitals are locked together, so the electrons can get locked together so their spins are always parallel to each other. This happens inside things like iron atoms and that. That's how you get standard magnetism in iron, sort of. So the total spin, individual electron spin is been, people call it spin 1/2. I won't really explain why. But its number is 1/2. And if I add these things together, the total spin is going to be an integer, a whole number of 1/2. So it's either a whole number or a whole number plus a half. So the total spin, when you make a magnetic atom, its spin is either a whole number or a whole number plus a half. And in 1981, I discovered that we were thinking about the spin 1 thing, which is made of 2 different spins. And we actually were interested in something called antiferromagnet, where the spins line up in opposite directions in their neighbors. And the standard state that people thought of at the time is a state which is not entangled. You could imagine assembling this state by just bringing these isolated atoms together for an infinity, and nothing much happened. I just brought them together and stacked them next to each other in this up-down pattern of their spins. And actually, what I discovered turned out to be completely against this paradigm of magnetism, where was just involved the ordering of the spins. And it turned out to be a state where the spins form these entangled pairs between their neighbors, and they get left off. And so you can think of this pairs of spins unlocking, and this one forming an entangled pair with the neighbor to the right, and the other one forming an entangled pair to the neighbor to the left. And actually, you see from this picture, when you get to the end of the chain, there's one left over that wasn't used. And there's a nice analogy for that. Suppose I have a row of people lined up. I assemble the people, and I entangle them by getting them to hold hands with their neighbors, right? When you form this chain, at each end of the chain, the ones in the middle can't move their hands because they're kind of linked together, but they're two hands that can be waved around independently, one arm at the end of the chain and the other arm at the other end of the chain. And those can be far away from each other. So you started off where the original rule was arms always came together, because an individual person has two arms which are quite close, but you made this entity where there was a left arm on one side and a right arm on the other side, and you didn't have to do any kind of violent, savage butchery to the people to get that. It was still alive, right? So that's somehow an analog for this thing. And it shows the kind of interesting edge states theory. So this was kind of a rather trivial thing, except it was totally against the picture that people had of magnetism, which is based on the first one I showed. And it's actually made my career partly because it excited so much anger, rejection, that people said had to be wrong. It was absolute nonsense, because they didn't really know about entanglement properly. So I just said this behaves this way, and they said it can't. Things don't behave that way. But in fact, we now know it was true, and in fact, my career was launched because experimentalists proved what I said was true, and science is facts, right? So it's not just a matter of opinion. Eventually, some measurements get done, and we know, this of course affects global warming and things like that. Whether global warming is true or not is something that could be established by measurement, and this property was established by measurement. And of course, when this eventually came out, people only had really two choices: the people who'd been strongly opposed and angry about it and publicly talking against it. They either had to come to the conclusion either they were stupid or I was brilliant. So you can imagine. So this was a great kind of. So the fact it was attacked so much was a fantastic plus for me, really. So anyway, this is the one they actually put on the picture of the Nobel Prize certificate. This is this little chain I tried to show you. Each one of us, this was supposed to be a certificate showing opening the doors to the mysterious world of topological matter or something. Each of us got a different picture with doors opening, and my door opening had this kind of magnetic chain behind it. Okay, so I'll just mention this is a much more significant thing, which was the second surprise, which I also contributed to a little bit. And this was a surprise that von Klitzing discovered this quantum Hall effect. And I don't have much time left, so I shall go rather quickly on this. But this effect was measured in a device that looks like that, right? So you imagine this looks like if your lab assistant ought to get fired if he does soldering like that, right? But actually, so this messy piece of junk produced this fantastically accurate measurement, which is basically measuring an integer, because this is an example of why the topological properties are really resistant to the dirt, right? This is absolutely not a perfect, clean device of like the silicon wafer or something, but this was still, the topological property was strong enough, that was stable enough that it could be measured in something that looks like that. So I'll quickly just say, in high school chemistry, we kind of learned that electrons go in an atom. You have a set of orbitals, so-called orbitals, and you have to fill them up. And you might have to have memorized 1s, 2p, 3d, and for the periodic table. So to form an atom, you get a set of these levels, and I have to put the electrons in. And because of the Pauli exclusion principle and the spin of the electron, they go in pairs in these orbitals. So that's what an atom looks like. In a strong magnetic field is what this quantum Hall effect was discovered in. Electrons go around in little circles. They're confined to a two-dimensional surface, this very messy two-dimensional surface you saw in the picture. And the magnetic field go through it. And in a magnetic field, charged particles want to move around in little circles. But there's a degree of freedom, which is where they the leftover degree of freedom is where the center of the circle is. So there are lots of possible centers for those circles. And as the quantum mechanics says their energy can only take certain values, so they can only move in circles of certain radii. So as in atoms, this gives rise to a set of states we can put the electrons in. We actually don't really need to worry about the spins too much because the magnetic field kind of splits the spin up and spin down energies. And if it's a clean system, the energy doesn't depend on where the center of the orbit is. So I have something like an atom, except I've got lots of, instead of one level or three levels or five levels, as in 1s, 2s, 3s, 3p, etc. Atoms, we have a large number of levels. And it turns out the number of possible independent states in each level is proportional to the area of the system. It's proportional to how much magnetic field goes through, how much magnetic flux goes through the system. So it's a definite number that depends on the magnetic field and the area. So to actually get this topological quantum Hall state, initially you might think you would get it by having exactly the right number of electrons to fill the lowest level and leave a so-called energy gap to the next level. It's like filling up the orbitals in an atom. And so if this was completely filled, you would actually get a cool formula that would actually explain what von Klitzing discovered in his measurements. However, this is to get the system to behave exactly this way, the number of levels depends on the number of electrons is probably fixed, number of levels varies the field, so you'd actually have to get the magnetic field exactly right so that there was just enough levels to accommodate all the electrons in the lowest level and none in the second. So this is absolutely the opposite of a topological explanation. And the magnetic field, the crucial thing what von Klitzing found is that he put his system he had a current running through his system, he switched on the magnetic field. You never get exactly the same magnetic field when you switch it on. It'll always be slightly different, but he kept the current constant. He always found exactly the same answer. If he'd done the experiment a different way, if he'd turned the current on, keeping the field fixed, he'd have never noticed his result. But he found he always got exactly the same thing, even though the field was never the same. And the actual answer turned out to be a topological thing. The electrons inside the sample go around in little circles, but the ones at the edge go around in little. The ones that are close to the edge will collide with the edge, and if they're going around in a clockwise direction here, they will go bounce, 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 and go around in an anti-clockwise direction. And since they can't complete their cycle, their energy goes up, and in fact, the energy level pattern should actually, counting from the center outwards, should look like this. And there's always some levels at the edge where you stop filling them. So this shows that this picture with the topological edge state shows that, in fact, that you don't need to get the magnetic field just right. There'll always be a gap in the middle if it's clean enough. So it took a long time to realize this, but this guy, who was one of my co-laureates, he actually came up, I greatly emphasized toy models where you can actually do a calculation. So the real system is very complicated, got messy, dirt and stuff in it, and he replaced it by a kind of very simple toy model with a periodic potential that you could actually knew how to do a calculation with, which wasn't realistic, but he found some huge formula. I won't say what it is, but this is the quantum mechanical, the direct analog of Gauss's formula after translating to quantum mechanics. Staulus didn't realize that. He just found the formula and didn't realize it was the same as Gauss's formula after interpretation, but a mathematical physicist put stuff together, and there was another thing called the Berry phase, which was discovered then. And these kind of discoveries for the first recognition of the topological nature of these new kinds of matter, the connection to deep underlying beautiful mathematics, and a completely new way of looking at quantum mechanics of particles in media. I can't emphasize how strongly the way we look at condensed matter has been completely changed by the discovery of these topological features and Berry phases and things in matter. So my last contribution on this was this was all thought to be due to strong magnetic fields. And in fact, although in retrospect, the Thouless formula doesn't really require a field, it actually requires something called time reversal braking. So time reversal braking means that if I took a movie of something and viewed it backwards, I could tell the difference, right? And magnetic fields break time reversal because the electrons go round in a given direction depending on the magnetic field. Change the direction of time changes the direction of the magnetic field, and they go around the other way. But magnetism also breaks that, and I came up with this kind of some toy model which turned out to be related to what people later discovered was graphene. In fact, in my paper here, I call this a model of graphite monolayer, but of course this is a total theoretical toy because no one would ever be able to make that. Of course, that was another Nobel Prize a few years ago when Gaiman Novoselov learned how to make graphene by putting scotch tape onto pencil lead and pulling it off and keep pulling it off till you just got down to one layer. So we never can predict what kind of amazing things are going to come out of scientific research in the future. But anyway, this toy model based on graphene showed this quantum Hall effect. I won't really explain what goes on. It had edge states and things. And the crucial thing is, I said before, the quantum Hall states have these signals that travel one way around the edge. And I guess my contribution, this actually, what I predicted in 1988 actually has just finally got realized. And it actually in China, as part of all this new money they're putting into condensed matter search, the Chinese people actually realized my thing, which was for a long time just a kind of a dream model. So this dream model of mine was actually generalized by other people to some other features, some even more interesting ways that led to what we now call topological insulators. But the original one is very interesting because it has these systems that go, you can have information traveling one way around the edges. And the analog of that is if you think what the freeway would be like if you didn't have a divided highway, if all the cars could, if there wasn't a rule of the road, which is, of course, drive on the right here, and of course in England to be different, it's drive on the left. But if people couldn't agree on which side of the road they were driving, there would be a total mess. And in some sense, when electrons flow down a wire, they can flow in both directions. So these kind of weird topological edge states can be actually used to separate stuff moving in one direction and stuff moving in the other direction to change a mess to a divided highway. And this has probably got, now it's actually being created without the magnetic field. It may actually have a lot of very interesting technology, and in fact magnetic fields are bad for superconductivity, and this stuff looks great with superconductors. And not just for that, it also turned out this principle of making things that travel one way around the edge didn't just work for electrons, it also worked for light. And this has also now been demonstrated, a kind of optical version. We proposed an optical version of this, and in fact, it's not been done with real light, it's been done with microwaves. It's been done on a centimeter scale rather than micron scale. But you can make you have these electromagnetic waves that travel around the edge of a sample, you put a barrier in the way, usually expect the barrier just to reflect them. But when things can only go one way, you can't reflect them they can't be reflected back off the barrier. So they just the energy just wants to keep on going, it just works its way around the barrier like a snake and keeps on going. So you can see there's a lot of possible technological uses of these very strange topological properties. So even more remarkable, which I'm going to, is generalizations where you can start to hide information in entanglement, and this is actually central to these new proposals for topologically protected quantum computers. This is not my work, but others have taken, so topological matter has taken off, this tip of the iceberg has led to all kinds of interesting things, and I won't go into this. This is something to do with what we might use for quantum computers. But I could just say there's lots more coming out. It's continuing to come out, and there's a great future. And it was actually an amazing experience to have been lucky enough to stumble over a couple of the things that led to the explosion of this field, which lots of different people are now participating in. Thank you.
All right, I think we have time for maybe a few questions. I'll let you sort of field them, and if you could maybe repeat the questions. So maybe we'll give just a second for people that need to head out, but then we can have a few questions and answers.
This picture is the doors opening on the unknown world. By the way, if anyone wants to see the thing, I have it here.
Okay. All right. So do we have any questions for our speaker?
So at the end of like the second last
Yeah, that's very technical, but it turns out that the original stuff was related to what we now call abelian topological quantum states. And I guess abelian means that if you add things together, they just kind of add up. Well, there's a new class which was discovered, even more fantastic class, which is called non-abelian, where you actually have some hidden states inside things that when you move things around each other, called braiding, you kind of influence this hidden internal state of the system, and that's where the quantum information gets stored. So it's a central thing to a lot of this proposals for quantum computing in a topological way. The big problem with quantum computing is to protect the information against decoherence. And to build, now people manage to build small things as a few atoms or ions moving around in a little trap and vibrating together. But a lot of those things are not scalable. If you actually want a practical quantum computer, you have to build something big, right? And many people think that the topological protection principle is the most logical route to building a scalable quantum computer. So there are many different attempts to build quantum computers right now. And, you know, if they do it, you'll be able to factor numbers, which in principle, a big one would break the codes for your credit card and everything. So you need a whole new scheme for quantum cryptography and things. But the small ones will be able to maybe find that what was it, 8 times 9 is 42, or whatever the Hitchhiker's Guide to the secret of the universe. But 8 times 9 is actually factorizing 42 is probably beyond the capability of the current things that people build. But factorizing 15 of 3 times 5 is within the practical calculation today of attempts at quantum computers. But you actually want to build a really big one, and the problems of this interaction with the environment just get worse and worse. And some people think this topological stuff and non-abelian states, one wrote to that, could be the solution to building scalable quantum computers which are protected against the information is hidden in a way that it can't be easily degraded. There's a lot of work on, I don't know that question, but the people who are trying to come up with a quantum theory of gravity, either string theory or something related to that, spending most of their time worrying about gravity and entanglement, in particular the entanglement near black holes and things like this. But the way gravity and entanglement go together is sort of an open question.
More specifically, suppose you have a trillion particles over there and another billion particles over here entangled. And the domain in between, are there reasons to believe that this region in between would manifest itself in some gravitational ring?
I honestly don't know the answer, but if you've got this, if you've got this separation, you've already solved the problem of the quantum computer by having this large number of entangled things. But yeah, there's a lot to be understood in this whole region.
You mentioned how electrons could have this time invariant symmetry under a changing magnetic field, and so that answers the question side. Could you entangle particles over the temporal function or the axis time?
I'm not sure I understand that question, but entanglement has generally been thought of as entanglement in space, but of course, from a relativistic viewpoint, you should whether things remain entangled. It's really two different particles, so I'm not quite sure how I would, in time, there'd be a single particle, but these are kind of questions one needs to think about. Now, time reversal invariance is actually the magnetic field causes the electrons to go in one direction. If you changing the direction of time, showing the movie backwards, the electron would go in the other direction. And if I looked at it, I'd say, oh, I could have also made that happen by changing the magnetic field from pointing from up to down. So time reversal, in that context, the magnetic field changes direction under time reversal, if you look at a movie. But yeah, I'm not sure what, but there's people studying all sorts of things about entanglement and issues to do with things that change in time and how they could be. But I don't know the precise answer to your question.
Other questions?
So, what advice would you give to someone who had a big on physicist and the community is kind of saying, oh, you're wrong, because I feel like maybe you should do that?
Yeah, well, of course, most of the time that happens, you actually are wrong. So the most important thing is to actually consider the possibility that you can be wrong, because that's the common resolution to the thing. But if you're sure of something, you should, you need to have, I suppose, some kind of self-confidence. I mean, I was confident that I was right, so it didn't really worry me. It was just annoying to me that people were attacking the thing. I guess there was some work that came out that seemed to contradict me about, I got 2 papers to referee about the same thing, which came out with a result that seemed to be on a modified model of a magnetism that seemed to be quite different from what I had predicted. And it did take me, and then it took me a little bit of time to work out what the hell was going on. And these were mathematically correct papers, so they weren't wrong, but it turned out that they tweaked the model of magnetism a bit in such a way that it actually, the regular behavior was the way I predicted it, but they did something. Topological properties are stable over some amount of deformation, and this model which contradicted it, they'd actually deformed the model sufficiently far that they broke the topological state that I discovered. So yeah, when this came to me, I had to scratch my head. Did I make a mistake somewhere? But in the end, I resolved it. That they were right and I was right, and they weren't talking about the same model of magnetism. They'd actually changed things sufficiently much to break the topological stability of the state, which I had. So everyone was happy then. It's a principle that eventually you will destroy these topological states by deforming them sufficiently far, and so yes, so you have to be confident. You have to, of course, have a realistic belief that you're right, right? So there's plenty of times when, but yes, you do need to have some kind of self-confidence to stand up for what. Listen to the rational arguments against you, and try and refute them, but you don't fold, yes.
Would you say that charged particles are a topological phenomenon?
Charged particles? No, well, charmed. Oh, I don't know. Charm is one of the attributes of quarks. There's a charmed quark, etc. So this is, charm is something like a charge. Well, actually, I believe in particle theory we've got 3 families of quarks, and charm is one of them. So most of the matter doesn't involve charmed particles, so these charmed quarks, but they were found by bashing particles together in high energies, and you find this. We don't really have any real understanding of the so-called standard model. We found a description of most matter, of the elementary particles, when we smash condensed matter up into little pieces, and then the atoms in little pieces. But no one really knows why the standard model is the way it is, and this is one of the big problems that was hoped. People were hoping to get more information out of this LHC, this huge colliding device in CERN, which discovered the Higgs particle. But we still really don't have any real understanding of why elementary particles are the way they are. What I was talking about has mainly been connected to electrons and atoms, much lower energy scale, but people thinking about topological states in particle physics too a great deal, and trying to see in string theory or whatever, can you think of analogs of this stuff. So in some sense, we're all talking about quantum mechanics. I'm talking about quantum mechanics on a very low scale, low energy scale, the matter that we're made out of. The particle people are talking about the quantum mechanics of very high energy particles. So there's some differences in the details of all these things, but in some sense, all this is quantum mechanics. So quantum mechanics is an overall principle that describes all kinds of different matter.
Okay, we have one sort of last thing to do before we finish up. We have a plaque to present you, which commemorates your lecture tonight. Okay. And along with your name on the end are all the previous 54 speakers, and you can spend some time glancing through them. I think you're in pretty good company.
There's some quite eminent people I see on that list.
Yes, indeed.
Yeah.
So
thank you so
we
much.
give that to you. Let's thank the speaker one more time.
It's got a big normal force.
Yes, he does. We'll send it to you. All right, thank you. Yeah, of course, you can set it right next to your Nobel Prize medallion. All right, thank you very much for coming out. Look for us next year. We'll have another one of these next fall.